Round 2. Section 11.2, area of triangles, trapezoids, and rhombi. I love the word rhombi, plural of rhombus. So, again, some of this you've already seen. Area of a triangle, 1/2 the base times the height. As we talked about with the parallelograms, the height is going to be an altitude coming from a vertex straight down. The side that intersects should be the base of your triangle. So here you see we've got the height, here we've got the base. The area of a trapezoid, remember trapezoid's a quadrilateral, one pair of parallel sides. Those parallel sides are known as the bases. So here you'll see the area of a trapezoid, 1/2 the height times base 1 plus base 2. So essentially I'm taking 1/2 of the height, again that's an altitude, I'm going to multiply that by the sum of the bases. Add these two bases together, multiply by the height, multiply by 1/2, and you've got the area of a trapezoid. Down here at the bottom, area of a rhombus. Rhombus, 4 equilateral sides, or 4 sides are all the same, making it equilateral. The area of a rhombus is 1/2 the product of the diagonal. So if I take this diagonal and multiply them together, multiply that by 1/2, and you've got the area of a rhombus. So 3 different formulas we have in this section. We'll take a look at a couple examples here in a second to kind of show you what's going on in terms of finding area. We'll also take a brief look at finding perimeter. Remember, perimeter is a distance around an object. So here we would add up all 4 sides. Here I would add up all 4 sides, add up all 3 sides of perimeter. You guys have a pretty good idea what's going on with that. So we'll hit on that as well. So a couple examples to take a look at. Example 1, pretty basic. You see we've got a triangle. We have a base of 10. We've got a height of 6. So our area, 1/2 the base times the height. So 1/2 times 10 times 6, giving us 1/2 of 60 or 30 square inches. Again, make sure that you're labeling your area with the proper units. We're talking about square units here, in this case square inches. In number 2, again, love the right triangles that we can bring into play here in terms of area. Here we've got an equilateral triangle. How do I know that? Because I see that this angle is 60, I see this angle is 60, so that means that this angle at the very top has to be 60 as well, which means if it's equiangular, it's equilateral. So if I know that one side is 12 centimeters, I know that each of these parts of the base are 6. So area, 1/2 the base, so that's 12, times the height. So again, hypotenuse, short side, long side, because it's across from the 60. So take 6 times radical 3, and that gives me the long side. So that's why we've got 6 radical 3 here for the height. 1/2 of 12 is 6. 6 times 6 is 36. So I've got 36 radical 3 square centimeters for our area of our triangle. In terms of perimeter, just real quick, equilateral is pretty simple. 12 plus 12 plus 12, we get 36 centimeters. Big thing to point out here, notice area, square units, in this case square centimeters. Perimeter, not square units, because we're just talking about the distance. You're not talking about what you can put inside, but you're just talking about the distance around the object. So here's just centimeters. In example 3, we start to take a look at the area of a trapezoid. Pretty extensive picture here. I spent a lot of time drawing it. I did almost major in art, but after my stick figure turned out horribly bad, I pretty much gave that up. So here you see we've got a base of 9 inches. I've drawn in both heights and altitude on each side here. Now, since these lines are parallel, these heights, these altitudes, are going to be the same length. So if I find one length of the height, I've also found the length of the height on the opposite side here. So notice that kind of cuts this into a rectangle. If we really wanted to, we could find the area of the rectangle in the middle and then add on the area of each right triangle here. That would be another way to take a look at it as well. I know that the total base here is 14 inches. How do I know that? Well, because I made it up. Over here we've got a little bit of a length of 3. Over here we've got a length of 2, so the 2, the 9, the 3 gives us our 14. Why did I set up that way? Well, to make it do more work, of course. This side of the trapezoid is 5 inches. Why is that important? Because now if I take that 3 inches here, the 5 inches here, I've got a right triangle. I can do some Pythagorean theorem that you'll see here in green that'll help me figure out the height of our trapezoid. So x squared plus 3 squared equals 5 squared. So we know that 3 squared is 9. We know that 5 squared is 25. If we subtract, we get 16. Take the square root of 16, we get 4. So the height of our trapezoid is going to be 4 inches. So that allows us to kind of fill in our formula now. 1/2, the height we know is 4. The sum of our bases, the top base is 9. The bottom base is 14. Does it matter which order you put those in? 9, 14, 14 plus 9? No, it doesn't matter. Half of 4 is 2. 9 plus 14 is 23. So if we multiply, we get a total of 46 square inches for the area of our trapezoid. The other reason why I kind of set this picture up so extensively is to kind of talk about perimeter of the trapezoid real quick. Again, perimeter, you just want to add up all the sides. So here we've got 9, here we've got 14 and 5, so you see we're adding up 9, 5, and 14. The big question mark again is, well, what's the length of that side on the left-hand side of our trapezoid? Don't know. Didn't give it to you. So, hey, look, there's a 2 here, there's a 4 right there, and that's a right angle. Pythagorean theorem. Gotta love it. So that's what you see right here. Hopefully, I wrote it big enough where you can see it. We've got 2 squared plus 4 squared equals c squared. So that's going to give us 4 plus 16, otherwise known as 20. Take the square root of that. 20 is not a perfect square. However, we can have some fun here and simplify it. Factors of 20 are going to be 4 and 5. I can take the square root of 4, which is 2, and so I get a side length of 2 radical 5. Draw that in. There we go. So that's why here you'll see our perimeter, 28 plus 2 radical 5 inches. If I needed to find an actual approximation, I could do that, change that into a decimal, add everything up then, and have my approximate perimeter in inches. So, something to keep in mind. Super. Not gonna lie, it's about 10:45 at night right now. Having fun, making some math videos so that you can watch them. Last one here we've got example 4. Drew a little rhombus. 4 sides all the same. Got a couple diagonals here, one in green, one in blue. You see here the length of this segment going from the point of intersection out to that vertex has got a length of 4 centimeters. Didn't give you the whole length of the diagonal. There's a reason to see if you remember that the diagonals bisect each other. So this is 4, this is 4. If this segment has a length of 6, then so does this one. It's kind of the definition of bisecting. You cut them in half. So, area of a rhombus, 1/2 the product of the diagonals. So this diagonal is 8, this diagonal is 12. We've got 8 times 12, which is 96. Take half of that. Our area is 48 square centimeters. Nice. The other thing to keep in mind, if I want you to find the perimeter, they don't only bisect each other, but they also form a right angle. So you've got 4, you've got 6. The question mark would be, what's the length of this side? Well, I'm so glad you asked. Pythagorean theorem. That's right. We could take 6 squared plus 4 squared, set that equal to c squared. 36, 16. That's 52 equal to c squared. Take the square root. Simplifying, because it's not a perfect square, we should get 2 radical 13. So I know that this side is 2 radical 13. I know that all 4 sides are 2 radical 13. So if I multiply that by 4, my perimeter would be 8 radical 13 centimeters. Hopefully you can see that over my fat knee. But that's good. That's what we should do. Pythagorean theorem. You ever see Mr. Bunner or Miss Shinko? Maybe Miss Pavlinda, Tom Thanks, Miss Schober. Thanks for teaching me Pythagorean theorem. I use it a lot. Especially with Mr. Kenner's class, because he loves triangles. They're fun. Alright. The only other thing that I could really show you would be something like this, where, once again, we're working backwards. If I know that the area of a trapezoid is, I don't know, let's call it 40 square inches. And I know that the height is 5, and I know that one of the bases is, I don't know, give me a number. Okay, 6. So that means we've got 40 equals 1/2 the height times base 1 plus base 2. Fill it in. 40 equals 1/2 the height is 5. Base 1 is 6. Base 2, I don't know. That's what we're going to figure out. So, how are we going to do that? Start multiplying. 1/2 of 5 is 2.5. 6 plus base 2. Distributive property. 2.5 times 6. Basketball hoop. Good. 15 plus 2.5 base 2. Subtract it out. We got 25 equals 2.5 times base 2. So if we divide by 2.5, we know that base 2 has a length of... I don't know. Not a clue. Yes, I do. It's 10. And that would be inches. 25 divided by 2.5. 10. So, something else to keep in mind. Probably another type of problem you may run into in terms of working backwards. So, good luck. If you got questions, rewind, ask me in class. See you then. Peace!